Okay, so let's take a look at 105. And this is a classification task different than what we've done before. What we did before was image processing, and this is going to be a little more abstract. So I'm going to just close, I suppose, file, move to trash, return, and new notebook. Okay, so we're going to download some data. This is data that came from the American census, I think. It's a bunch of handwritten numbers. And so once it's come down, we're going to want to look at it. This will show us the structure of the data. And I can put this in, but I'm not going to run it until the previous one finishes. You can tell from there, it's circling around and still counting up 19 seconds. So, okay, good. It's done a handwritten digits with 784 features. Okay. And then we can get a summary of the data here. So this is X. X is the images. So it's a whole list of 784 numbers and a variety of them. There are a total of 70,000 images. Each one of them have 784 pixels. And then Y is the labels. So this is labeled data to train them on. And each one of those images is a single digit, and they tell you which digit it is here. So the first one's a 5, the next one's a 0, and so on. So we have the data here to do supervised learning. And let's take a look at some of these images. So here, this will plot some of them. There. So that's just what we expect, just handwritten digits. All right. Now we can play a few games learning how to classify these. The simplest thing is to train and test based on this. So here we define a model. Or we're just going to split the data into training and test. There's 70,000 images, so we're going to take 60,000 for the training set, and the test set will be the remaining 10,000. So that's simple. Okay. And now we're going to make a simpler task. The original task involves sorting them into 10 categories, 0 through 9. But for this, we're going to settle for a binary decision. So we're just going to have 5 and not 5. So that's what this is going to do. It's going to make a simple data set marking all the 5s as true and all the others as false. All right. And therefore, there's 10 times as many false as true, because this is all the other digits. So it's not evenly distributed. But anyway, we have a labeled data set for training and testing. And now we can make a model. So we're going to make a simple linear model. So the input image comes in with all those pixels here, and they just go to a neuron, and it takes a linear combination of all these. No hidden layer here. This is a very simple model. So this will make a stochastic gradient descent model, which is what we've been using. That's the one that takes little steps in the direction that will make the arrow go down. So that's what it does. It defines a stochastic gradient descent classifier. There's a random series of steps, but you can specify the seed, so the random numbers are always the same, and that's handy for teachers. So I can give people instructions to run this code, and it will have exactly the expected effect at the end instead of varying randomly like one of the ones we did earlier. So it's defined it, now it's fitting it. It's choosing how many epochs to train by itself. And I think what it usually does is it keeps going until the error goes up. So there should be, I think the norm is some kind of measure of error that's going down. Here's loss. That's probably rare. So loss is 122, 111, 105, 96. Loss is still going down, 84, 81. Okay. And this is a recommended procedure, and that's just what it did. See, here's the loss going down, down, down. Oh, no, here it went up. Okay. I thought it would quit as soon as it went up. But maybe it did something a little more complicated, like take some kind of average. But usually what you do is you go down, down, down. When it starts going up, you know you're done. You've hit the minimum. So it converged, taking 25 seconds. And here's what it predicts. The 5 is true. The next 2 are false. So you can see those 3 predictions are correct. It's true. This is a 5. false, these are not fives. Okay, so that's not. Now, to measure the accuracy of a model, one common technique is cross-validation. What you do is you split the training data into 3 groups, and you train the model 3 times on 2 of the groups and try to predict the third. So that's what you do to see if the training data is consistent. That's called cross-correlation, and then you'll have an accuracy score. So now it's got to do 3 times training, which we saw it takes about 30 seconds for each cycle of training. Looks like it's reached the next cycle of training, starting again at 0 seconds. Okay, so it's done, and we get 3 accuracy measures, 95%, 96%, and 96%. So that's pretty good. The 3 folds are all equally good. However, that's not as good as you might think, because remember, the data is 90% false. So if you had a model that just always said false, it would be 90% correct. So 96% correct is not as great as it sounds. So another way to rate the quality of a model is the confusion matrix, which shows all the various options of right and wrong, like a truth table. So it's going to do 3-fold cross-validation, return the predicted values, and then it's going to count the hits and misses. And we'll get an array down here. All right, and I may not bother with all of these in live. There's the array. So this shows the non-5 images in the first row. The model correctly called 53,000 of them non-5, but it incorrectly called 687 of them 5 when the actual image was not 5. In the next row, here's the 5s that were correctly counted 5s, and here's the 5s that were incorrectly called not 5s. So those are the 2 kinds of errors. All right. Now you can define precision as true positive over true positive plus false positives, and define recall as true positives over true positives plus false negatives. There's various, and there's something called the F-score that combines these. These are just various ways of statistically boiling down the quality of your model. And the F-score will only be near 1 if both precision and recall are high. So you can calculate all these things and see what you get. And you can adjust it. What happens is the model doesn't actually put out an output of true or false. The model puts out a number, a floating point value. And then you have a threshold where you say above that value, we're going to call it true, and below that value, we're going to call it false. So you can adjust that. You can make the threshold low, and that will push the errors to one corner of the confusion matrix. And you can make it high, and it'll push the errors to the other. And if you go to the middle where precision equals recall, that's sort of the central value. So you can choose. And this is something that happens also with biometric controls. If you have something like a fingerprint reader, you can set it to be really strict so that only fingerprints that are 100% or very good are let in. And then what happens is you have very low false accept rate. People who are not authorized cannot get in, but you have a high false reject rate. Sometimes the people that are authorized can't get in because their fingerprint is a little bit off and doesn't match. It's the same kind of thing here. All right, so you can view the raw neuron output here, say the first 12 images, and see what this looks like. And see, that's the point. The image, a big number means it's likely to be a 5. A small number means it's not a 5. So the 5 here is 4,700, and the 5 here is 2,100, and the rest of them are below 0. So a threshold near 0 would work pretty well, but you could adjust it. And by default, it uses a threshold of 0. So you can just try it with different threshold values. That's what this is going to show us. So you can customize the model to meet your requirements. So when this is done, it's going to give us a nice graph like this, which shows that as the threshold increases, you increase precision, but you decrease recall. And so the other, you can also go the other way and eventually reach a point where the denominator is nearing zero, so you get noise. Anyway, those are just statistical measures of things. And now let's move to multi-class classification. So if you wanted to actually sort it into all 10 possible categories, there are various ways to do it. And the way it runs it by default is the 1 versus 1 strategy, where it compares 0 to 1, 0 to 2, 0 to 3, 1 to 2, 1 to 3. And that's 45 possible binary classifiers to compare each digit with each other digit. And so that's a pretty complicated mess, but that is one way to do it. And there's that graph we were just talking about. Let's go take a look at this one. All right, so it's going to run 45 binary classifiers, and there you go. And it's only going to be, it only made 3 mistakes. And one of them was image 80. Image 80 is actually a 9, but it was misclassified as a 0, 1, 2, 3, I think. No, see, this, and not classified as 8. The biggest number is here, 8. So it can be misclassified as an 8. As a 0, oh, pardon me. Oh, 0 is 9.27. Okay. It's a 0. It's most likely to be a 0. And the next choice is maybe an 8 and maybe a 9. So image 80 is pretty confusing for it. All right. And if you do 1 versus the rest, which is the other strategy, where you do 0 versus not 0, and then 1 versus not 1, and 2 versus not 2, so you're only going to have 10 classifiers combined to do this job, then, whoops, missed the F. There. Then what you're going to get is it's only going to get 2 of them wrong, 48 and 80. So it's comparable. These are all doing pretty well. All right. And then you can do stochastic gradient descent to classify the images into 10 categories, which is, I think, the one we used before for these 10 images. Those were 1 versus rest classifier and SVC, which is C-support vector classification, they call it, which is going to use the one with 45 pieces. But this is going to be the one that has 10 output neurons, I think. The one we used to classify those images before were images of clothing. And so now each one of them gets a probability, an output score here, not a probability, and you look for the largest number. So here, I think it's minus 166 is the largest number. They're all negative. And that's a 0, 1, 2, 3. And here's 5, which is almost the same. Oh, 5 is bigger. No, 3 is the biggest. 5 is the runner-up. The right answer is 5, and it got it wrong. And here's another one. That's 5. Minus 3, oh, minus 264, so it thought it was a 4, and so on. So you can see what it got wrong. All right. Somehow I didn't get the same answer as before, but that's because I did 500. Oh, I look at the wrong picture. That's why. Okay, here we are. There. It contained 5 errors in the first 500 training images. All right. So this model seems to be a lot better. These other models were only looking at 100 images, and they were getting 2 or 3 wrong. This one's only getting 5 wrong in the first 500 images. So that makes it look better, but you're going to see it's overfitting. That was performance on the test data that it trained on. Here's testing it on that test data that we set aside before, and it got 91 of them wrong out of 500. So it's overfitting. It's fitting the detailed random features of the training data in ways that do not generalize to the test data. All right. And so you can do cross-validation with 3 folds. And if you do that, you'll find it's 80% accuracy in each fold, essentially. And then you can scale the inputs and recalculate it, and the accuracy increases only a little bit, so that's not too bad. And I'm not going to bother doing it all live. You can make the confusion matrix of this, which is pretty complicated. This is the predicted label and the true label, and on the diagonal are all the correct ones, and here's all the various types of errors you can make. So it looks like the 13 and the 13, those are pretty common errors. Here's a 15. So it has a high chance of predicting 7 when the right answer was 9. So the 9s sometimes look like 7s. That makes sense. And on you go. You can try to understand these things. And you can normalize it with percentages if you like. So that's an example of the details of classification classes and how you rate classification tasks. So I'm going to stop this recording.